Okay, as I said several times in the video, here is the maths explainer. First up, relative humidity. Relative humidity is fairly straightforward. Relative humidity is the amount of water vapor in the air divided by the maximum amount of water vapor the air can hold multiplied by 100. So relative humidity is in percentage terms. This means that changing the amount of water vapor in the air or changing the maximum amount of water vapor the air can hold, in other words, changing the temperature, will cause a change in the relative humidity. Okay, so as the temperature rises, the maximum amount of water that the air can hold increases. And we can see this on a graph. Here we've got a graph, we've got temperature along the bottom, and up the side we've got the amount of water that the air can hold if it was 100% humidity. And this is measured in grams of water per kilogram of air. And the graph looks like this. Now in the video I talked about the idea of ventilating the boat, letting in the cold air outside to replace the warm, moist air that's inside the boat. And in that example I talked about the boat being at 20 degrees centigrade and a relative humidity of 50%. So if we look at the graph, 20 degrees centigrade, and we go across, that gives us about 15 grams of kilogram of air. It's 50% relative humidity, so that's 7.5 grams of water vapor per kilogram of air. Now, in the example I gave in the video, I said that it was 5 degrees centigrade outside and 80% humidity. So how much water vapor would be held in the air under those circumstances? Well, at 5 degrees, what we would then have for 100% humidity is we'd have about 5 grams of water per kilogram of air. And as it's 80% relative humidity, that would be 4 grams per kilogram of air. If we let that air into the boat and then we warmed it up to 20 degrees centigrade, what would now be the relative humidity of that air? Well, we use the equation that we saw earlier. We plug in the value for 4 grams, which is the amount of water vapor in the air that we've just let in at 5 degrees centigrade. We know that at 20 degrees centigrade, the maximum amount it can hold is 15 grams, so we plug that in. And when we do the maths, we get a relative humidity of 26%. So by swapping that air over, we've reduced the humidity inside the boat of 50% and reduced that down to 26%. This also means that the air in the boat can now hold more water, so it can help actually dry the boat out, because we've effectively got, if you want, that 24% spare that we can get the dampness inside the boat, the condensation out away from those surfaces and hopefully into the now drier air. So relative humidity is the amount of water vapor in the air divided by the maximum amount. Now, another way of expressing this is by using pressure. So relative humidity is equal to the actual vapor pressure of water in the air divided by the saturation vapor pressure at the same temperature. So that's another way of expressing relative humidity, and it just makes the maths a bit easier because you don't have to convert between the vapor pressure and the amount. Now, this saturated vapor pressure can actually be calculated, and I'll put a link through to the paper that shows you how to calculate this in the description. The link's on the screen now here, but the equation is shown here. And this is in fact equation 17 from the paper, and it works for temperatures above 0 degrees centigrade. If you want to go below 0 degrees centigrade, you use equation 18. But anyway, in this equation, what we've got is we've got the saturation water vapor pressure, and we have the temperature, which has to be above 0 for this equation to work. And if we know the temperature, we can easily calculate the saturation water vapor pressure for that particular temperature. So let's have a look at a worked example. Here's our equation again. It looks quite complicated, but it's not as complicated as first appears. The temperature is at 20 degrees centigrade, and we just put that 20 degrees into the equation for T. And when we do that, the equation now becomes this. We then start to solve the equation using BODMAS, PEDMAS, whatever you want to call it. And basically we just walk through the calculation. As we walk through the calculation, at the end we come out with a saturation pressure of 2,339.16 pascals. So that is the saturation vapor pressure for air at 20 degrees centigrade. Now, what happens with temperature change? Let's have a look at that. So let's say again we got my boat at 20 degrees centigrade, relative humidity of 50%. What would be the relative humidity of 10 degrees centigrade? In other words, what I'm saying here is I've gone to bed at night, it's 20 degrees on board, it's 50% humidity. What will be the relative humidity on board when I wake up in the morning? Well, we can just plug these numbers into the equation. And here's our starting equation. Here I'm doing it for 20 degrees, calculating through, and as we've already seen, it comes out that the saturation pressure is 2,339.16, and that's 100% relative humidity at 20 degrees centigrade. For 50% relative humidity, that figure drops to 1,169.58 pascals. It's just 50% of it. Think back to the earlier equation. If we then look at what happens at 10 degrees. Now I take 10 degrees, plug that in, do the maths again, and what it comes out is the saturation pressure at 10 degrees is 1,228.2 pascals. We know that relative humidity is the vapor pressure divided by the saturation pressure multiplied by 100. So if I put in the 1,169.58 pascals, which is the vapor pressure at 20 degrees and 50% relative humidity, we then divide that by the saturation pressure at 10 degrees, which is 1,228.2 pascals, multiply that by 100. That means the relative humidity is now 95.2%. So basically, as the boat is cooled down overnight, going from 20 degrees centigrade down to 10 degrees centigrade, the relative humidity on board will increase from 50% to 95%. There's been absolutely no change in the total amount of water in the air, but the relative humidity has changed because the air can hold less water. Now, the other thing I talked about earlier in the video is the dew point, and this is the temperature at which water vapor hits 100% relative humidity, so it will start to come out, it will start to condense on surfaces. And again, we can do some maths around it. For this we need two papers, and again I'll put the links below in the discussion, and here are the two papers here. One of them just gives the formula, the other one gives some key sort of constants that are used in the formula. The formula looks a bit confusing, but basically what it is saying is that the dew point Ts is equal to the temperature and the relative humidity multiplied by some constants. And the two constants, that B on the top of the equation is 243.04 degrees centigrade. This is something called a Magnus coefficient. I've no idea how that's derived. And the A in this equation is 17.625. Again, this is referred to as the Magnus coefficient. Again, I've got no idea how that's derived. Now that funky little bit that says alpha brackets T comma RH, that actually resolves to this, which is the natural log of the relative humidity divided by 100 plus A, which is 17.625, multiplied by the temperature T, divided by B, which is the 243.04, plus the temperature. So what you do is you resolve for that part of the equation first, and then you plug it back into the top bit, and that will give you a dew point. So let's have a look at a worked example. So the boat is at 20 degrees centigrade and relative humidity of 50%. What would be the dew point? Well, this is our equation, and the first thing we need to do is solve for that alpha T comma RH bit. So we just plug in the relative values into this, remembering that we've got these Magnus coefficients to go into it as well. So when we do that, this is our equation. We start putting in the values, and what we get is that the alpha T comma RH is equal to the natural log of 50, the relative humidity divided by 100, plus 17.625 times 20 divided by 243.04 plus 20. And then if we just work through the maths on that, what we come out with is that the alpha TRH is equal to 0.647. We then take that value, which is 0.647, and we plug it back into the original equation, the TS equation, And what we get is TS is equal to 243.04 times the alpha TRH divided by 17.625 minus the alpha TRH. When we put the numbers in, what we come through to is TS is equal to 9.26. So the dew point is 9.26 degrees centigrade. So that is the temperature at which, on a narrowboat, if it's 20 degrees centigrade and relative humidity of 50%, 9.26 degrees is the temperature at which that water will start to condense out on your windows and your metal frames, etc. Anyway, that's the basic maths that's behind a lot of the stuff that I've been talking about in this video. I didn't want to include it in the main body of the video because it may not be of interest to a lot of people. I personally find it interesting. Hopefully you've found that interesting and useful. I'd like to thank you for watching and listening to this. If you've got any questions, please feel free to leave them in the comments. That's a lot. Bye for now.